Thank you. And thank you. And I'd also like to thank the organizers for the invitation to participate in this conference. A privilege to be part of this conference in honor of Sergio. So I first met Sergio as a graduate student in 1995. And I think for the next few years I was very intimidated by him. He can be very intimidating to graduate students. And but of course afterwards I started learning from him, and he's very generous. And now we are colleagues, so it's a great privilege to be part of this conference. So I'm going to talk about problems that are not directly related to his work, but in some sense the point of view, it's connected to the kind of things that he's done in terms of the point of view is connected to the kind of things that he's done in terms of regularity of solutions and the time of existence. So there are several concepts that we have an evolution, and we are trying to understand it on longer and longer times of existence and prove things about the evolution. Now I'm going to talk about the very concrete problem, the water wave problem. But first, because it's somewhat it's maybe not so well known, I'm going to introduce the problem and make it into a very clear evolution, to connect it to very clear evolutions. It starts, one can think of it, one can think of the picture. So the way the picture starts, one starts with a fluid. So the water waves, we have a fluid that lives under an interface, and we have an evolution that both the fluid and the interface move. So that's what the system is. And they move, so the fluid, the velocity field moves according to the Euler equations, and the interface, so the Euler equations, Vt plus V grad V is minus the gradient of the pressure minus the gravity. There's also an additional component having to do the waterways, namely the gravity pointing down. And then the free interface moves in a way that's moved by the fluid. So if you have a particle on the interface, then it's going to want to move the interface along its velocity. And one can also put, in the presence of surface tension, one can put the pressure on the boundary, and the pressure is prescribed on the boundary. If you want to understand how all these things coming together, just to understand why is that we need, for example, the pressure on the boundary and not everywhere, so how does this make sense? If we were to solve the equation very naively, so assume that we have an interface and the velocity at time t is equal to 0, and we are looking for an incompressible fluid, then we can take the divergence in the flow, and then we get the equation delta of the pressure is equal to some kind of grad of V squared. Which means that the pressure, if we are to know it on the interface, we would be able to construct it everywhere by solving the Dirichlet boundary problem. And then once we know the pressure, we can calculate the grades and things like that. So we can basically understand the entire situation at time t is equal to 0, and then d by dt of v is going to tell us how it moves to the next time, and then one has to make sense of this as a well-posedness theory. So that's how the equation makes sense. So for example, that's why we need to prescribe the pressure on the boundary. Now there are natural questions. This is an evolution equation. It's a little more mysterious, but it's an evolution equation, and there are natural questions. The most important one, of course, is the local regularity, and that's very well understood by now. But just like for many other evolution equations, we understand the local regularity, but of course we understand much less about the dynamical formation of singularities, and we understand much less about the long-term regularity. So these are the two main topics. There's one other topic that's special to water waves, and I just wanted to, it has to do with steady solutions. They're very pretty pictures, and they go back a long time, more than 150 years ago. They're very, very pretty pictures that have to do with the construction of steady solutions or traveling solutions, or basically steady solutions of the waterway system. And there are also variants that one can have. One can have, for example, boundary conditions. So here I just drew the simplest picture, but one can have boundary conditions, periodic boundary conditions, meaning that the bottom would be periodic. The vertical direction is not periodic, but the bottom would be periodic. One can have finite bottom, so one can have a bottom at so one doesn't have to go all the way to infinity. One can have two fluid models in which we have one fluid here and another. That doesn't have to be coupled with vacuum. It can be coupled with other things. So there are many situations of this type. And so the main topic that we are talking about is the long-term regularity in a kind of a special situation. Now I'm going to say a few things about the other parts, which are very well understood. The local theory is well understood, but it's not so simple. So the first like clean results were obtained by C.J. Wu in 1997, 1999. There's been a lot of work. It's not so simple to make sense of this picture that I said, because you also have the interface and the velocity and the regularities that one has to work with the two objects there. They have to be matched. You cannot assume that one of them is smoother than the other. One has to match them. And it's not so simple to do the well-posedness theory. The general well-posedness theory was done by CJU in 97, 99, and there's been a lot of work. There's some work before in some special cases. There's been a lot of work afterwards, extending it to all sorts of to many scenarios. The general statement that I didn't want to write a theorem, but the general statement is that one has local regularity, and the time of existence depends on two things. It depends, first of all, on the smoothness of the initial situation, but it also depends on this R-chord constant of the interface. If you can imagine that the interface could have looked like that, where the water was here. And then because it's almost self-intersecting, then the time of existence has to account for the fact that the solution cannot go for too long without creating a self-intersection. So these are, and there are more recent results that I didn't write here. There are more recent results that have to do with low regularity. One can also one can also address this question, low regularity. It's not possible to get the critical regularity. The critical regularity is at the level of C1 for the interface. There are no results of this type. One can get to C3/2, for example, or things of this sort, but not to C1. So C1, it's in all dimensions. In Sobolev space, it would be something that depends on the dimension. Now, the singularities, it's also a very big topic. So the singularities, formation of singularities for water, it's a very big topic. And there are two ways you can form singularities just by looking at the picture. One of them is to form a singularity inside the fluid, but that can only be addressed after you form after you understand the same situation for Euler. It can only be harder if you have a moving interface on top of the Euler equations. So there's no real understanding on that. One can have a singularity at the interface. So that's a different kind of singularity. One can have a singularity in the interface, and the only one that's known is the splash singularity, the so-called splash singularity, which is this picture. One starts with a situation that's very close to being self-intersecting, and one can arrange the velocities on this almost self-intersection in a way that it leads to a singularity. So that's a theorem of Castro, Cordoba, Fefman, Ganset, and Gomez-Serrano, and then separately by Coutin and Scholler. Now, it turns out this splash singularity, it's only for the water wave system. It's something that the singularity happens while the interface is still smooth, but it self-intersects. It turns out that cannot happen if you have any fluid in between here. So that's a theorem that I proved a few years ago with Charles Pfefferman and Victor Lier. So it shows that this one still would, the more likely singularity, more stable singularity, be something that would also form a corner. The picture, the simple picture to understand is that if you have a fluid in between, then there is no way for this fluid to get squished. While if these two things are to go smoothly towards self-intersection, there's the fluid in between doesn't have time to escape. But it's still possible in. Oops. It's still possible in principle that one can form a corner at the same time as singularity. That's what I think happens. But it's not known. So that's an important open problem. Formation of singularities through corners, for example, that's not known. And then the last topic, the last of these general topics about waterways is about the steady solutions. The most famous one is the Stokes waves. So they go back to before 1850, so they go back almost 200 years. There are special solutions, and there are many others. So there are many others. So I put dots because there are lots of theorems from the 1900s, some from the early 20th century, and now there are more recent ones from just a few years ago. So there are lots of special solutions that one can construct, and they are traveling. They are very pretty. They also open problems that have to do, for example, with overhanging situations, and those are not well understood. But in any case, so our goal is to understand to understand long-term regularity. It is possible. So for this system, in a very special situation, it's possible to construct global solutions, and global solutions. So there's been some work a few years ago that I was part of it as well. So it goes back to work of CJU, Germain Masmoudi-Chatin, Fabio Pusateri and myself, Alexandru Delors, Efim Tataru, Wang, and also some other work that I've done with Deng, Pusateri. So there are a few special situations we can prove that small and smooth and localized initial data lead to global regularity. All of these situations, I'm not going to go through all of them, but all of these situations, in all of these situations, one needs to be in the irrotational case, so without any vorticity in the system. And one also has to be in the entire domain. So these are two requirements in all of these situations. There are other, the other things, whether we put surface tension or not, they're in 2 or 3 dimensions. So those are, there are a few variants, but all of the global solutions, they correspond to the situation where we are in the irrotational case and we are in the entire space. Now, in the periodic case, one can get long-term solutions. Of the type that if the data is of size epsilon, then the time of existence would be epsilon to the -2 or epsilon to the -3. Or in some of these theorems, like for example, if the result of Berti and Delors, in some case one can get epsilon to the minus an arbitrary power. But that's not my, so that's work we've done a few years ago. That's not my point. I just brought it up as a long-term regularity result. That's kind of very close. It's closely connected to the kind of work that Sergio has done for waterways. Like, for example, of course, we use vector fields. We also have to use Fourier analysis because it turns out that there are certain certain resonances that can only be described well in terms of Fourier analysis. So the problem. Now I'm going to start stating the exact problem that we are looking at. So we're talking about irrotational waterways. In the setting of irrotational waterways, so you're looking at the domain, we have the same picture that we have there, except that if we are irrotational, then we can describe the entire situation. Being irrotational means that the velocity field is a gradient. And the velocity field being a gradient, afterwards we have a function, and we can also restrict the function to the interface. And then there's the potential, so you restrict the potential to the interface, and that's the primary variable. So in the irrotational case, one can state the theorem in a more transparent way, in which we have two functions, h and phi. This is in all dimensions. So h and phi. H is the height, and phi is this velocity potential restricted to the interface, and they satisfy a coupled system that's of the form dth is gh phi. And dt phi, now dt phi, all of those terms in the right hand side, they are velocity terms. So one has like v grad v, when we start expanding in all the various components, v grad v becomes those terms in the right hand side. So we have the right hand side, we have something to do with the gravity, so the first term, and then something has to do with the other velocities, and there's also the surface tension that comes in. And the equation looks more like a pretty standard dispersive. It turns out to be dispersive. Looks like a pretty standard dispersive equation. It's not so transparent because we have the Dirichlet-Neumann operator. So this gh phi, it has to do with the fact that we had to understand the pressure, for example. We know it on the interface, but we have to understand it everywhere. And that's not an operation so that goes through this Dirichlet-Neumann map associated to the domain. So this is the system that we have. I'm going to describe it in simpler terms so to understand exactly what it does. And it turns out that there's a conserved Hamiltonian. One can write it in terms of these variables. Originally, the conservation takes place in terms of the velocity field, but once we write it in terms of these variables, we get a conserved Hamiltonian that has 3 parts. Then it has a dynamical part, and it has so the first one, so gh phi dot phi. This is at the level of grad phi squared, grad to the 1/2 phi squared, and the other one is a potential. So it has several parts. This Hamiltonian, and these are all conserved along the evolution. This is the so-called Zakarov formulation of the waterway system. Now, what do we want to do? So this is the Zakarov formulation. Now, what do we want to do? What we want to do is to understand the so-called, to understand rigorously the wave turbulence theory of water waves. And it's a very classical problem that in mathematical physics that goes back to work of Hasselmann and Zakarov from the 60s. And it's a key part of what's called the Hasselmann model of climate variability. So Hasselmann model of climate variability, Hasselmann is not a mathematician, he's not an oceanographer. And he developed this theory to try to explain the climate basics, to try to explain the weathers, like the dynamics of the weather. So it's been, it's very much used, even, I mean, parts of it even are used today. Hasselmann got the Nobel Prize for this theory. So much of the theory that is developed is attributed to him. Now, Zakarov is a mathematician, and he's done a lot of work on the mathematical side, a lot of work at understanding the level of understanding the wave turbulence. Now, the wave turbulence problem. So we
was completely independent. They never intersected.
No, they never. Zakarov was a mathematician, so we had a different point of view. The equation itself that's derived is called the Zakarov equation. At least that's how we see in the wave kinetic equation. Now, so this wave turbulence has received intense attention in recent years. Now, the problem is the following. So I'm going to describe it in a way that's very easy to understand for those of us who do evolution PDs. We are looking at this. We are looking at this evolution. You can think of it. That that's basically the cubic NLS. We are going to see the theorem for the cubic NLS. It's not exactly the cubic NLS, but pretend it was the cubic NLS. Then the situation is the following. The rule, the difference between this and the usual theorems is that you can only assume smallness at the level of the L infinity norm. Nothing is small at the level. No energy is small. Of course, if you put weights, it's not small. It's the picture of the ocean that locally the perturbations are very tiny, but the ocean is huge. So all the L2 norms, everything has to do with the L2 norms is going to be huge. And we want to understand the theory, we want to understand the evolution, a long time of evolution, just starting from the fact that the perturbations are small in local energy. You can put local energy or you can use L infinity norms, it makes no difference. But that's all we know, that the norms are small in L infinity. Of course, L infinity norms, they are not propagated properly by this kind of flows, neither by the Schrodinger equation nor not by the waterways. So the only way you can make sense of the problem a long time is if we have randomness at the same time. So the energy is big, but because we have a lot of randomness at every mode we have independent randomness, the L infinity norm is small. And if we could propagate randomness, in principle we could say that the situation stays the same, that the energy is going to be big, but if the solution were to stay random, then because of the randomness, the L infinity norm or all the local norms would be small, and that would allow us to control the evolution. So that's the picture. The different rule compared to, for example, what Sergio knows very well and what he introduced many of us to, is the fact that the energy is giant. There is no control at the level of, no global control. Everything, the only thing one can control in terms of small objects are at the level of local energies. So that's. Okay, so that was just a rough, just a description of what we want to do. So the wave turbulence received a lot of attention in recent years, and it's been mostly done for semi-linear models like the Schrodinger and the KdV equations. There's a core difficulty. There's a core reason why semi-linear is different from quasi-linear in this case. In this work of Buckmaster, Germain, Hani, and Chatat, the work that's most closely related to what we do is the work of Deng and Hani on the cubic NLS, Colo Germain, Transafilani. And the focus has been on understanding the wave kinetic equation for these models. So now I'm going to describe the theory for the cubic NLS because that's easy for all of us to understand. The cubic NLS is a very transparent equation, just the most you can take in any dimension. The sign of the nonlinearity doesn't matter here. It's all, I just took the plus sign, but one could have taken the minus sign as well. So it's I dt plus delta u is u times u squared. And the setup is we are looking on a giant torus. The torus has to be very big in order to have enough randomness. So looking on a giant torus. And the kinetic theory, so what we are looking to understand is the amplitudes. So the situation is what I said, the initial data, so I wrote it here. Oops. So the initial data is written here. It's of this type. It's written in such a way that it has small, so this is the dimension d, it has small L infinity norm lambda, assuming that we have randomness in these coefficients. So lambda is the L infinity norm of the initial data. And then
are the eta mean 0?
I'm sorry?
Do the eta have to be mean zero? Or?
No, the eta don't have to be mean zero. And that's, but they all have to be independent from each other. So completely independent. Every eta is, every Fourier coefficient is completely independent from all the others. And that's, so the point of the construction of Deng and Hani is that if you start with data of this type, then one can construct the solution on a time. So the kinetic time scale on which you need to understand the solution in order to be able to derive the wave kinetic equation is this lambda to the minus 4. So there's an important number, lambda to the minus 4 as opposed to lambda to the minus 3 or lambda to the minus 5. So the number there is very important. And if one can construct the solution, for the cubic tendency there's not the issue, but one has to control the solution on this very long time of length lambda to the power minus 4. Then one can define, so one can take the average, so one can take this, so one can take the Fourier coefficients, and the expectation is the expectation of the Fourier coefficients over all the possible data, and the square of that, and then there's this quantity n, the quantity n that's this average Fourier coefficients, and the point is that this so the derivation of the wave kinetic equation, I didn't write the wave kinetic equation, is dtn is this kernel that depends on n, n. So it's a kernel, it's an explicit kernel that it's trilinear in the variable n, and it basically picks up the resonances of the original system. That's if I were to write it, you see how the resonances come in, but that's what it does. So it picks up the resonance of the original system. And then the point is that there's a lot of information on this slide. The only one that matters, however, is the time of the length of existence. So everything else, in some sense, follows, provided you can construct the solution on the time length being lambda to the power minus 4. So the real issue in all of this, and what took time to develop, because there were many other constructions before the work of Deng and Hani, which didn't hit the whole time of existence. Now, if you don't hit the whole time of existence, then the kinetic wave equation doesn't make sense, because you see there's a dilation here that you have to dilate the times. The times in the original variable is not the same time as in the kinetic wave equation. And one can do this, so this has been done. So the resulting equation is the Zakarov equation. This dtn is a kinetic equation, but it's homogeneous. It's the analog, if you want, of the Boltzmann equation in the context of this particle. Some analog, one of the possible analogs of the Boltzmann equation in this particle situation. One can do these things for particles as well. One can do these things for so there are many equations of this type, and we've seen a lecture yesterday. There are many equations of this type one can derive. There's only one thing that for me, like the place that the main thing to understand is the time of existence. One has to control the solution of the original equation. In order to get anything, one has to control the solution of the original equation up to time lambda to the minus 4. And if you control the solution up to time little constant times lambda to the minus 4, this means derivation of the kinetic wave equation at time 0 up to the little constant. So that's the logic of the problem. And
this K. How do you get the K?
So the K, I didn't write it down. I should have written it down. It's basically the resonance system. So you restrict to the resonances of the system, and it becomes kind of like a Boltzmann kernel, except there are 3 of them.
You don't assume random phase at time 0?
Yes, you have to assume complete randomness at time t is equal to 0, and the issue is, of course, you have to show that you preserve some form of randomness.
Then the average of eta is 0 if you have random phase.
I'm sorry?
If you have random phase, then the average of eta is 0.
The average of eta, okay, maybe it's 0, yes. The average is 0, yes. Yes, the average of eta is 0, but the independence is important. The independence of eta versus all the other etas. So eta of k, it's independent from eta of k prime at time t is equal to 0. Of course, at time t is equal to 0, you know this perfect randomness, but the issue becomes, what does it mean randomness at higher times? Because you have these nonlinear collisions, and that's the core of the core of the analysis. And one can do, so how is this done? So what is hard and how is this done? One has to expand the issue is how do you propagate this randomness? We have no simple way to, first of all, you can never have perfect randomness at any other time because you start having collisions. And then what does it mean that we have some kind of randomness at any other time? And the only way we know how to do this is to expand it. And we expand it, so Deng Honey, they expanded it in this, so you start expanding the duhamel formula, and then you have to keep expanding because originally the U's at the first level, the cubic U's here, they are not the same as the initial data, but you have to keep expanding them. Everything has to be expanded in terms of the initial data, and then the theory becomes understanding how all of these Feynman diagrams, understanding efficiently all of these Feynman diagrams. And if you want to hit the entire time of existence, that's a critical problem. So one really has to expand. One has to expand up to any order, up to an arbitrary order. One cannot stop at a finite time and start measuring there. So that's what, and that's what they've done for the cubic NLS. Now our goal is to try to understand to initiate a similar investigation for irrotational water waves. Now there's a fundamental difference because water waves are quasi-linear evolutions, and in quasi-linear evolutions, the first step doesn't work. You cannot expand. You cannot understand the solution as there's no duhamel formula that provides the solution because you lose the derivative. And if you keep expanding it, you lose more derivatives. There is no stopping that. So that's so one cannot. We have this problem that we don't have a method to get it started, to get it off the ground. So in particular, as I say, so that's what I'm saying here, that there's unavoidable loss of derivatives if one was to use the duhamel formula. And this means that the solution cannot be described as using iterations of the duhamel formula. And to address this, we have we propose a new mechanism that addresses that, at least in part, able to address this. And the mechanism consists of two steps. Firstly, at the highest order of derivatives, we can only prove energy estimates. We cannot track randomness at the highest order of derivatives. So we can only prove energy estimates. The point is that we have to control the growth of the energy, and the growth of the energy should only be growing. The energy should only be growing in terms of quantities that have a chance of being small, and the only quantities that have a chance of being small are the infinite norms of the solution. So the point is to get control of the energy in terms of L-infinity based norms, and so this is the first step in the energy estimates. And then the second step, we want to, so you should think that basically the growth of the energy is controlled by kind of like the small frequencies, and those small frequencies in principle we can say that they preserve some form of randomness, and then because they preserve some form of randomness, we would have control of these L-infinity norms. So that's the first step, and the second step is we have to prove things about the small frequencies, that indeed they do preserve this form of randomness that would allow us to close back the argument in terms of the so to close back these two steps. And at the level in the second step, we can think that we are in a kind of like bounded frequency regime. And at that point, we can start using the duhamel formula because we need to be able to say something about how we preserve randomness. So now I'm going to state the two theorems. We have two theorems. So I'm going to state the two theorems. The first one is an a priori estimate. So we are saying, so what we are saying is you are looking at this specific system. So you're looking at the specific system being the gravity water wave system in 2D. So the dimension at the level of the interface dimension is 1, and the surface tension is 0. And this is the system, I just rewrote it. And what we are saying is that if we control uniformly, so we control the energy, it turns out that the energy in these variables, the correct form of the energy is in terms of age and greater to the 1/2 of the potential. That has to do with the fact that we start the velocity and restrict it to the interface. So this is the right way to measure the two things together. And what we assume is that we have control of the energy on a time interval by a constant A. And we assume that we control the L-infinity norm with a few derivatives, so W dot n10 of the same variable by a constant epsilon that depends on t. And then the conclusion is that we control, so if we were to have this a priori control, then you control the solution at the final time, So we control the energy at the final time by the energy at time 0 plus a quintic increment. So the point is the quintic increment is the last term in the right hand side there, and it's a squared, and then the quintic comes from the fact that the increment is controlled by epsilon of s to the power 3 as opposed to the power 2 or as opposed to the power 1. So the power 3 is the one that matters. So as I said, the point is that we control it in terms of the L infinity base norm to the power 3, and also it's important to use only the L infinity norm. So in this quantity that controls the growth of the energy, we should only use things that we in principle could control later in terms of a small quantity, and that's the L infinity norm. So epsilon is only something, it's only a local kind of energy. So quartic energy estimates have been known, in which instead of having the power 3, we have the power 2. It turns out that one could use those two, but those will lead to a weaker theorem. What we prove is that what we are able to prove for this particular system is this quintic energy estimate. And this is nothing to do with randomness. At the end of the day, the whole theorem is about understanding randomness. The hardest part is understanding randomness. The one that I'm presenting here is not about randomness. These are general estimates. It's only motivated, so what we are allowing to have control in the right-hand side is motivated by the fact that we want to address the random problem. But the proof itself depends, it has to do with resonances. If we think of the equation, originally the equation, the quadratic equation is of the form dt plus I dx to the power 1/2 u is equal to n of u and u bar. So the dispersion, it's not exactly the dispersion that you'd see, for example, for Schrodinger equations, but it's something that works the same way. And it turns out that it doesn't have, there are no quadratic resonances, because one can do a simple calculation that if we were to look at the quadratic resonances, they only happen at 0, and at frequency 0, it turns out there are some multipliers in the nonlinearity, the analog of the null structures for wave equations, which dominate those. So this will only prove a quartic energy inequality. Now, for the particular system we are looking at, we want to prove a quintic energy inequality. So we have to, after we normalize the problem, so we remove the quadratic resonances, we have to do the same thing for the cubic resonances. And the cubic resonances, they come in two types. We have the cubic resonances that are the trivial resonances, because you always have this kind of cubic resonances in cubic problems. But there's a Hamiltonian structure, the Hamiltonian that I put earlier, that allows us to deal with that. And there's one more type of resonance, the so-called Benjamin-Fair resonances, which are explicit. They happen for this particular system. So they're explicit. There are resonances that are of the form, it's a two-parameter family of resonances of the form one. There are 4 frequencies, they add up to 0, and the phase themselves, they add up to 0 in the right way. And so these are resonances that happen at the level of, so this will be cubic, at the level of the cubic equation. So these are quartic resonances. And it turns out that for this particular model, it's an algebraic miracle for this particular model for the gravity waterways in 2D. The contribution of this resonance is 0. There's a big multiplier that takes a long time to calculate, but it turns out that the right places on the set of resonances, it turns out that multiplier is 0. And that's so that was an algebraic fact that was known to Diachenko and Zakarov from many years ago. And based on that, from 30 years ago, based on that, Zakarov actually thought originally that the gravity waterway system is integrable, because one has this amazing cancellation at the next order. It turns out it's not integrable. So it turns out that one has to stop there. At the next level, there's no more cancellation at the next level. So our main contribution is to make sense. So this is an algebraic calculation, but our main contribution is to make sense of it and put it into an analysis and get exactly the L infinity norm, get exactly control of the energy in terms of the L infinity norm. Now, as a corollary, if we are to assume much stronger smallness, so much stronger smallness. So once we have the quintic energy inequality, we can get without using randomness, we can get a long-term of existence theorem. So if we are to assume a stronger smallness, a smallness in terms of Sobolev spaces, then the conclusion that we have is that we have a time of existence of length. So rho is the size of the initial data, and we get rho to the power minus 6. At least when r is large enough, is rho to the power minus 6 is the time of existence. So we start to data such rho, and we get to the time of existence rho to the power minus 6. And there's been some work trying to understand the problem in this setting. So the rho to the power minus 3, one can get it on a bounded domain, on a bounded torus. So that was done by Berti, Feola, and Pusateri, and then C.J. Wu in the Euclidean space. And there was another result, rho to the power minus 4. But what we can do with the full quintic energy inequality, with the correct increment on the energy, we can get rho to the power minus 6. And it uses basically, it's a simple proof because it uses the L4 L infinity x Triquartz norm, which is the correct norm for this situation. And that's the one that we use to measure the increment. The L4, the fact that you have L4t, that leads to the power 6. If we were to have a Triquartz estimate L3t, L infinity x, we would have probably gotten almost global regularity. Okay, but in any case, so now I wanted to get to the main point, namely the random problem. So this is the same equation. The equation I wrote it the same way, and we are looking at this particular variable. So here I'm going to be a little bit less precise. So you're looking at the same variable u. The correct variable for the waterway system is u is equal to h plus I times greater to the power 1/2 phi. And we are considering, initial data of the form epsilon times r to the minus 1/2. So these are normalizations. We are on a big interval of radius r. These are normalizations that amount to the fact that the initial data has L infinity norm about epsilon, and it's uniformly distributed everywhere. So the L2 norm would be of the form epsilon times r to the power 1/2. And that's the etas. So the eta k of omega, they are the independent, identically distributed normalized complex Gaussians. And so this is the initial data, and the theorem is the following: that if we have, so I'm stating everything just in terms of time existence, mainly because you are not able to hit such a long time in order to be able to say anything about the derivation of the wave kinetic equation. But we can still prove something on a long time of existence. So the issue becomes on how, given this situation, on how long of a time of existence can we control the solution. And what we are saying here is that you can control the solution if the parameter r, so if the parameter, the length of the the length of the domain is sufficiently big, you can control the solution up to time epsilon to the power minus 8/3 plus a little bit. So that's so this is the main theorem. So that's where it's this power that comes in at the end. That's the main result. The fact that we have control of the solution on this time epsilon to the power minus 8/3. By the same kind of procedure that I said. So this is the second part of the proof. We already have energy estimates, and we want to be able to use we already have energy estimates, and we want to be able to think that the low frequency, we want to say that the low frequency still preserves some kind of a randomness that ultimately keep the solution at L infinity norm not too big, and that's the one that we put back with the energy estimates. So that's what we would like to set up. And
so before you were talking about epsilon to the minus 4, right?
That would be the desired result. So that's been done. We are obviously short.
Right, so it works only in the semi-linear case.
For now, it's only known for the Schrödinger equation. For the Schrödinger equation, high dimension, not even known for the Schrödinger equation in one dimension is not, in two dimensions is not known. You have to take something else in one dimension because it's completely integrable. But it's really only known, and it's only known for a few years for the cubic NLS in high dimension. Epsilon to the power minus 4. It's very hard to get epsilon to the power minus 4. If you think in terms of these L infinity norms, if you think of it, so you have a cubic equation. The natural growth is epsilon to the power minus 2, because you have a cubic equation. So you have two terms of size epsilon and then multiply by the energy, so you get epsilon to the minus 2. And the only way you can get epsilon to the minus 4 is if you can get a completely clean square root cancellation. But the square root cancellation is very hard to get it. and it has to be completely clean also. You cannot lose anything. It's very hard. So the epsilon minus 4 has been it's only known in that case. In our case, that's what we end up with, epsilon minus 8/3. I'm going to try to explain by comparing with so that's what I'm going to do for the remaining.
And also, I mean, all the equations that have been dealt so far are cubic in the nonlinearity, right?
Yes, one can do quadratic. For quadratic, in certain ways it's easier. For quadratic, you're only aiming for time epsilon to minus 2. You aim for twice what would be, you aim for twice because of the square root cancellation. You have to aim for twice in order to derive the wave kinetic equation. You have to aim for twice the deterministic time. So that would be, I don't think it's been done up to the end point. It's only been done for the cubic NLS and for a shorting for a certain type of.
But if it were for the non-NLS, presumably it will also for the wave equation.
I don't think it's been done. It has to do with the resonances. So the resonances are different. The resonances are different for the wave equation. I don't think it's been done. So the Schrödinger equation, it's kind of like the base model, or the model that Tran and Stafilani had. That's another model. It's kind of like a KdV equation, multidimensional KdV equation. Okay, so that's now I'm going to try to compare. So as you see, the theorem, our theorem it's comes short, so you're not hitting anywhere close to epsilon to minus 4. In my mind, we're using the time of existence as a proxy, because if you cannot hit the full kinetic time, then you cannot derive an equation, but it's a proxy in order to be able to to understand what methods work better. So if one could get a little longer time, that would be better. And that's how things develop for the cubic NLS as well. So it took a long time to get to epsilon to minus 4 to pick up all the ingredients that are needed. Okay, so I'm going to compare. I'm going to describe the solution. I'm going to describe some of the ingredients in the proof in a way that compares mostly with the cubic NLS, and try to understand how we can make sense of things. So first, we are thinking. We are thinking of an approximate solution. So I think of the equation, the truncated equation. So what we are doing is we are looking at a new variable, WTR. And what we are doing is we are taking all of we are truncating the equation. We are truncating the high frequency, and we are truncating in terms of the number of, the equation is neither cubic nor quadratic. It has an infinite expansion, so we are truncating in terms of the number of variables. And so this equation is obtained by performing a normal form. And at this stage, you notice the loss of derivatives, they don't matter, because we are truncating in terms of the frequency. And we eliminate the higher order nonlinearities, and we truncate frequencies higher than, lower. So we remove the frequencies higher than R to a certain power.
So the philosophy, if I understand correctly, is that the causal linear nature of the equation is fitted at the level of energy.
Yes.
And then you go below, where we treat the problem like a semi-linear problem.
Yes, that's what we would like to do. So it's kind of like the same thing that you do if it was just in the deterministic case. You have an energy at the highest order, and that's driven by the low frequencies. So you need to understand more about the low frequencies than about the high frequencies morally. So that's and then at the level of the low frequency, we have the ability to lose derivatives, and because we can lose derivatives, we can start proving randomness. We cannot prove randomness using the Duhamel unless we give up on derivatives. So that's kind of how we try to put it together. Okay, so here I have a proposition that it's not written very precisely, but the proposition basically says that if we have good control of this truncated, have good control of this truncated solution, then we can get good control of the full evolution, provided you also have the energy estimates. So if you have the energy estimates, it's a bootstrap that we have there. So if you have the energy estimates, and we have control of this truncated solution, then we can get control of the full solution. And now the truncated solution, it looks of this form. We are truncating. So keep in mind the frequency. So the time. There are these two parameters, epsilon and r. And the time that we are aiming is epsilon to the power minus something like minus 8/3 in our case. R is very big, but the truncation happens at R to a small power. So the fact that we truncate, there's some loss in R at the level of the truncation, but it's gonna translate to losses of epsilon at the end. So you can compare this. You can compare this pretty faithfully with the cubic NLS. So the cubic NLS is IDT plus delta IDT. So IDT plus delta dt minus I delta u is minus I u bar u squared. So the loss of what I'm saying here. So there are a few things. The loss of derivative is small compared to epsilon to minus 1 because we arrange it this way. And it turns out that the higher order terms, they're not much harder than, they just lead to more complicated graphs when we do the expansions, because instead of having trees that have, instead of having simple trees like ternary trees, we have to look at general trees, but morally they are not harder than the cubic terms. Now, so I'm going to describe some of the ingredients that we need to understand. So the linear dispersion. So the linear dispersion, everything has to do with the resonances. So to understand the problem, we need to understand the resonances. And the linear dispersion for the water wave equation is this c to the power 1/2. Now we cannot do number theory for c to the power 1/2 because it's impossible to say how would you write a number, how would you write 0 in terms of combinations of this type. But we don't have to do it because what I'm saying is that as long as our parameter r is large enough, then we never have to do number theory. As long as the sets that we have to look at are sets of this type in which c to the power 1/2, maybe with various signs, are in a given interval. And as long as these densities as long as these frequencies are dense enough, then the volume of these sets is the same. The volume of these discrete sets is the same as the volume of the continuous sets, which can be calculated. So my point is that we can avoid completely number theory, which would be impossible, by thinking that we are in a kind of a scaling law in which the parameter r is allowed to be bigger than the parameter epsilon. So I wrote the exact numbers here. It's actually exactly of this type. You can see that the volumes in the Euclidean space, they're not hard to calculate because everything can be calculated one variable after the other. But understanding which ones of those points are integers, if the sets were thin, it would be very hard. But if the sets are wide, then the number of integers is the same as the volume of the set. So you can go around that. Now there are several issues that come up. It has to do with the renormalization. In order to be able to, for the cubic NLS, it's very important to do the renormalization of the first resonances. So there are these basic resonances that I wrote them here. It's a frequency k. If we have k, k1 minus k1, that goes to k. So that's the most basic, there's the stronger resonances. One has to renormalize them. In our case, we also have to renormalize them, but there's no simple normalization of this type. And we have two choices, none of them too good. Because one choice would be to renormalize all of this frequency in terms of the solution itself. But the problem is that the coefficients of the solution itself, they are random, and everything has to be, at the end of the day, we still need to look at to get the square root cancellation. So if we were to have a phase here in which the coefficients depend on the coefficients of the solution, then we wouldn't get the square root cancellation. We end up renormalizing them in a weaker way. We renormalize them in a deterministic way, and then we still get some benefit from that. So we get a normalization. So we get a renormalization in terms of this function gamma. Now that's an extra issue, namely the original equation is not cubic. We don't get to write it as a cubic equation. It's a quadratic equation. And so what's the right variable? For some things, the right variable is the original variable. For some other things, is the normalized variable. So we don't have a very clear. So we have to make some choices. It turns out that the graphs themselves, because the original, we end up working in terms of the original variables. But then the graphs themselves, they have two types of nodes. So we have a kind of a more complicated tree in which we have the nonlinear trees, like the usual trees, and then each one, some nodes, they could have this the so-called n branching nodes. So the normal form branching nodes. So that's that's something that has to do with our understanding. The problem is not so clean. We don't have a very good variable to work in terms of. And finally, it's a dimension 1 problem. And the dimension 1 problems, there's an issue that actually becomes the final issue that gives us the final time. It's a dimension 1 problem. There's certain structures. So everything is based on understanding these big expansions and organizing these big expansions. There are certain structures, certain interactions that are worse in dimension 1, and they are the ones that lead to the final time of existence. Those are not understood as well in dimension 1, even for simpler problems. Even for the so-called MMT equation, it's a semi-linear model in which one doesn't need to do all of the energy part. Even there, they are not understood in 1 dimension. And there was an earlier result of Vasilev who proved the time of existence of size epsilon to minus 5/2 for the corresponding MMT equation. So in our case, you're able to prove that there are various chains of interactions that prevent us from going farther than epsilon to minus 8/3. Okay, so I'm going to end this. So I'm going to this is my last slide. So I'm going to just have a summary. So the wave turbulence is wide open. It's an important problem in some sense. It's the wave turbulence theory. To me, it's mainly about water waves. One can do other models as well, but it's mainly about water waves. It's an important problem, but it's we are very far from understanding it, and it's more difficult. I think it's substantially more difficult in the case of the semi-linear case. Mainly because the first step, one cannot start the first step right. One has to use energy. The Duhamel formula cannot be used to describe the solution due to loss of derivatives. And what we do is we use time of existence as a proxy for wave turbulence. Because we don't understand many things. We don't understand, for example, what are the right variables. It's unclear what the right variables. So what do you measure is the right way to measure? You can measure the size of the coefficient square and take the average, but you can also measure other things that have to do with the coefficients. Maybe they have the similar sizes, but one could measure the solutions in different ways. So we use time of existence, and time of existence that we get in this theorem is epsilon to the power minus 8/3, as I said. So I'm going to stop here. Thank you, and happy birthday, Serge.
I have a question. At the deterministic level, is the absence of Fourier resonances essential for proving the improved energy estimate?
Yeah. If those were there, you wouldn't get. They would contribute.
So if there are, say, infinite many Fourier resonances for some model, then it's not possible to derive this kind of energy estimate, right?
No, for us, the quintic energy estimate is part of the model. So if you are in a different model, you have to do something else. If you are in a in some sense, the quadratic models are you could say they're easier because you only aim for time epsilon to minus 2. So there it would be a different picture. But for us, in order to get the theorem at the energy level, we need to have no contribution from those resonances. Yes.
What is the prediction by physicists for the, say, turbulence spectrum or kinetic equation?
The kinetic equation itself is a little mysterious. So the kinetic equation, because there are lots of derivatives, the well-posedness of that is also mysterious. So we didn't get to the kinetic equation time. It could be that basically that by itself is not well-posed, and that's the reason why it cannot be derived. So I don't know, because we have no path to getting to the full kinetic time.
If you consider a kinetic equation like the Zakarov equation, for instance, you have lots of derivatives. So this is not really an obstruction to get an equation. Maybe to prove it, but...
To prove well-posedness, I meant proving well-posedness the kinetic equation. That is not known for this model. Whether one can derive it formally, but it's not known if that's well-posed.
And what it looks like? If it's
In some is known, in some time, but the equation is known.
So one can derive it formally by looking at resonances. One can derive these equations formally, but there's always going to be a loss of derivatives, which it's not clear that you can prove that that equation itself is well-posed.
Yeah, that's why I asked what this equation is.
We never got to the point of understanding that equation. It's not derivable, and it could be a physical thing that one cannot derive it because it's not well posed, and at the same time is not relevant for the long-term dynamics. That could be also the picture, as far as I know. Yeah.
Can you detect any kind of transition to high frequencies or growth of Sobolev norms in this regime?
No, there is no growth of Sobolev norms. That's basically that's what we want to say. We want to say that there is no growth of Sobolev norms. On this time, then there is no growth of Sobolev norms.
Thank you.
For the Duhamel formula part, is it possible to conjugate the equation with a series of suitable transformations to bring the coefficients into constant in X so that you can have some sort of Duhamel formula?
Maybe. I don't know. Maybe. I mean, that's the first result of this type. If one could get a better understanding, maybe. It's a one-dimensional problem, so you could imagine maybe it's possible to get some kind of constant coefficients.
Yes.
We haven't done that, so I don't know if it's possible or not. So putting it in terms of time of existence, so one can have, in principle, a better proof to get a longer time of existence. That's how things develop for the cubic analysis as well. It took some time to get to the epsilon minus 4.
Okay. If there's no more questions, let's thanks Alex.
Thank you.